Hello everyone! In this session, we shall revisit the concept of limits. In Calculus 1, we have discussed about limits that result to the indeterminate form 0 over 0. And to solve for such limits, we made use of either factorization or rationalization to simplify the given before evaluating the limits. In this session, we shall learn about a rule that helps us find or evaluate limits that are of the form 0 over 0, or in fact, even infinity over infinity. Perhaps you could remember that limit of sine x over x as x approaches 0 is equal to 1. This does not mean that when we plug in 0 for x, this will give 1 as a result. In fact, if we plug in x, then sine of 0 over 0 in fact is meaningless. And this one is our indeterminate form. But what do we mean by limit of sine x over x as x approaches 0 is equal to 1? This means that when we plug in x values that are very, very close to 0, the value of this gets closer and closer to 1. In calculus, we have a rule that allows us to evaluate limits such as limit of sine x over x as x approaches 0 in a different manner. Now, if you want to find the limit of sine x over x, we try differentiating the numerator and then the denominator. Okay, so this one becomes the limit of, we differentiate the numerator, derivative of sine x is cosine x over derivative of the denominator, derivative of x is 1 as x approaches 0. Take note that the resulting limit will no longer end up with 0 over 0 because of the denominator 1, which means that we can now evaluate the limit. And the limit of cosine x over 1 as x approaches 0 is, we plug in 0 for x, cosine of 0 is 1 over 1, so the result is 1. Okay? So the answer is 1. This solution made use of a rule in calculus called Hopital's Rule. Hopital's Rule states that given two differentiable functions, f of x and g of x, on an open interval a,b containing c, the functions are differentiable everywhere on that interval except possibly at c itself. Now assume that g prime of x is not equal to 0 on this interval if the limit of f of x over g of x as x approaches c produces an indeterminate form 0 over 0, then the limit of f of x over g of x as x approaches c is equal to the limit of f prime of x over g prime of x. This means to say that if we end up with 0 over 0, to evaluate its limit, we can differentiate separately the numerator and the denominator. Okay, f prime of x is the derivative of the numerator, g prime of x is the derivative of the denominator. And take note that it works not only for 0 over 0, but also for infinity over infinity, negative infinity over infinity. And that we will be able to show in the next or in the succeeding examples. So let's go back. It works for limit of sine x over x as x approaches 0. We have shown that a while ago. Limit of sine x over x as x approaches 0 is equal to 1 after differentiating the numerator and the denominator and then evaluating the resulting expression here, we ended up with limit equal to 1. Take note that it also works for infinity over infinity and the negative infinity over infinity. So it does not only work for indeterminate form, 0 over 0, like in the case of limit of sine x over x as x approaches 0. It also works for infinity over infinity. For instance, the limit of the natural logarithm of x over x as x approaches infinity. Both numerator and denominator are getting bigger and bigger. So we don't know what's going to happen. So we have to apply the Hopital's rule. Okay, so let's try evaluating that limit using the Hopital's rule. Limit of the natural logarithm of x over x as x approaches infinity. So this is the case where our numerator gets bigger as well as our denominator. Okay, so it's still indeterminate. Okay, this is still considered to be an indeterminate form. So just like what we did in the previous example, we have to differentiate both numerator and denominator. And so this becomes the limit of x over the derivative of x is 1 as x approaches infinity. Okay? Or the limit of 1 over x as x approaches infinity. And you know that this is equal to 0. Okay, this is equal to 0 because when the denominator gets increasingly large, okay, as it approaches infinity, the quotient of 1 over x becomes so less that it approaches 0. The L'Hopital rule was first published by the French mathematician Guillaume L'Hopital. He is credited with the writing of the first textbook in differential calculus in 1696. And the book contains the L'Hopital rule in it. Let's solve more applications of the L'Hopital's rule. Okay, so let's proceed to example number 1. Evaluate the limit of e raised to 2x minus 1 over x as x approaches 0. First, you have to determine whether the given is in the indeterminate form. So if we plug in 0 for x, e raised to 2 times 0, that's e raised to 0, 1 minus 1. So we have 0 in our numerator over 0 in our denominator. So clearly, this is of the indeterminate form. And so we have to use L'Hopital's rule to evaluate its limit. So to apply the L'Hopital rule, we take the derivative of the numerator. So this one gives the limit of the numerator. The limit of e to the 2x minus 1 is 2e raised to 2x over derivative of x is 1 as x approaches 0. So this is now simpler than the previous because its denominator is no longer 0 but 1. So now we can evaluate 2 and then e raised to 2 times 0, that's e raised to 0 over 1, which when simplified is equal to 2. Okay, now we proceed to example number 2. Number 2, limit of 1 minus cosine x over x squared as x approaches 0. By direct substitution, again, we shall end up here with 1 minus 1 over 0 squared or the indeterminate form 0 over 0, which means that we have to apply the L'Hopital's rule to evaluate this limit. Okay, so to evaluate, we simply differentiate the numerator as well as the denominator. Take note that this does not make use of the quotient rule. So we have to differentiate separately the numerator and the denominator. So taking the derivative of our numerator, derivative of 1 minus cosine x, is x is negative. Sine x times the negative sign here gives sine x over 2x as x approaches 0. However, the resulting limit is still equivalent to the previous limit because if we substitute x with 0, then we'll have sine 0 over 0, which is still of the indeterminate form, which means we have to use once again the Hopital's rule. Okay? So, in here, we made use of the Hopital twice. So, we differentiate once again the numerator and the denominator. We take the derivative of sine x, which is cosine x, over derivative of 2x is 2 as x approaches 0. So, let's go back. First, we differentiated the numerator and denominator. However, we ended up with something which is equivalent to the previous, or it's still in the indeterminate form. Because if we plug in 0 here, then that's sine 0, 0 over 2 times 0, 0. So, it's still indeterminate. We have to apply once again the Hopital's rule. So, differentiating our numerator gives cosine x and derivative of our denominator is 2. So, this one makes sense now. This is now equal to cosine of 0 is 1 over our denominator, which is 2. Now, we proceed to example number 3. How about the limit of the square root of x times e raised to negative x as x approaches infinity? Here we have two quantities. One which is the square root of x and e raised to a negative x. The first part here increases without bound because x approaches infinity. However, the second factor or the second part, which is e raised to negative, by virtue of the negative sign, this part here decreases. What's the limit then? So we have to, before we apply the Hopital's rule here, we have to express the given as a quotient. Take note that in the previous examples, okay, all of them are ratios or quotients. And so in this problem, we have to express it in terms of a numerator over a denominator. Okay, you know for a fact that this could be written as limit of the square root of x over e raised to x as x approaches infinity. And now we can apply the Hopital's rule because we now have a numerator and a denominator. The derivative of the square root of x is 1 over 2 square root of x over the derivative of e to the x is e to the x as x approaches infinity. We can rewrite this as limit of 1 over 2 square root of x e to the x as x approaches infinity. And this is no longer 0 over 0 because our numerator is already 1. And so, if this one gets bigger and bigger, as well as 2 square root of x, okay, as x gets bigger and bigger, then what happens to the quotient 1 over 2 square root of x e raised to x? The quotient gets too small that it approaches 0. So the limit of the square root of x e raised to negative x as x approaches infinity is equal to 0. We proceed to example number 4. Let's look at the limit of the quantity 1 plus 1 over x raised to x as x approaches infinity. For problem number 4, we let y be equal to the quantity 1 plus 1 over x raised to x. And we take the natural logarithm of both sides. Ln of y is equal to the natural logarithm of the quantity 1 plus 1 over x raised to x. This could be simplified as ln of y equal to x from your laws of logarithms, okay, power law, x logarithm of 1 plus 1 over x. So now we are going to express this into a quotient. Is there a way by which we can express this into a quotient? Yes. ln of y is equal to ln of the quantity 1 plus 1 over x all over 1 over x. This is equivalent to the previous. Now we are going to take the limit. The limit of ln of y as x approaches infinity, and we shall work on the right side of the equation, is equal to the limit of ln of 1 plus 1 over x all over 1 over x as x approaches infinity. So applying Hopital's rule, we differentiate both numerator and denominator. So this now becomes limit of our numerator is ln of the quantity 1 plus 1 over x. So this one takes the form ln of u. Okay, ln of u. Remember that if y is equal to ln of u, then y prime is equal to 1 over u times du. So we have to apply that in our numerator. Limit of ln of 1 plus 1 over x is 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, which is, take note that 1 over x here is the same as x raised to negative 1. And therefore, its derivative is negative 1 x raised to negative 2, or that's negative 1 over x squared. So times negative 1 over x squared all over. We now differentiate the denominator. X raised to negative 1, just the same, gives a derivative of negative 1 over x squared as x approaches infinity. Take note that this is common to both, so we can get rid of it right away. And therefore, this is reduced to limit of 1 over 1 plus 1 over x as x approaches infinity. So this is no longer of the indeterminate form. So let's look at how this behaves as x approaches infinity, or as x gets increasingly large. So if x here gets increasingly large, what happens to this ratio? This one gets closer and closer to 0. And therefore, limit of 1 over 1 plus 1 over x is equal to 1. Okay? Is equal to 1. So let's go back. Limit, therefore, of ln of y as x approaches infinity is equal to 1. The question is, what has an natural logarithm value of 1? What must be y? Okay, what must be y? Which number has a natural logarithm of 1? It's the number e. Okay, y must be equal to e. Okay, y must be equal to e. Therefore, the limit of the quantity 1 plus 1 over x raised to x is equal to e, the constant e.